Integrals. We took a look at integrals, by the way, back to that map, right? Maybe I wasn't quite done with this yet. We took a look at some integrals in vector motion. We kind of applied integrals to motions in space and 2D plane and 3D space. And so we did some of that stuff. But now we're going to take integrals of multivariable functions, and as different from the vector valued functions where we only had one variable t, when we're dealing with multivariable functions, we have, well, multivariables, more than one variable. And so we have to figure out how to deal with that. And then that's when we'll see it become a double integral and later on a triple integral. So just to get us started thinking about this integral business, let's take a look at the components of an integral. And the corresponding geometry. So when we integrate, we usually say what we're going to integrate over. And so we identify this as your domain or limits of integration. And that relies on knowing the domain of the function. So the a and b are all in the x-axis. And then we're looking at the height value, at least geometrically. We're taking a look at this flat on the xy plane. We're looking at the height of this. And then we have the differential dx. Okay, so those are the basic components. And there's a lot of ways to say this. We say the integral from a to b of f of x dx. Sometimes we say the integral of f of x dx over ab. That's actually what we're gonna, the phrase that we're gonna want to remember now for integrals. Integral of f of x dx over the interval AB, and I'll put the interval we can actually take out, so just say the integral over AB. So if we say it that way, then we're going to say, we can get used to saying that the of is what's inside of the integral, the over is what we're integrating over. So we can also say the integral over the interval AB of f of x dx. Anyways, if we get used to that language and saying it that way, then we can easily transition to our double integrals. All right, here's our first definition of double integral. So a double integral is written as two integral signs, and then with a little sub r next to it. And then now we have our function of several variables, two variables to be more specific, and then we have a dA. dA. If the limit exists, then if the integral does exist, this function is called integrable. All right, so let's try to break this down a little bit or a lot and see what it is they're talking about here. So, first of all, we could say in words, integral. Sometimes we say of f of x dA over r or over r of f of x dA. It doesn't matter. So I'll switch the language this time from our previous one over the region r of the function f of x y dA. So instead of the interval AB now, we have to change our notation to include a whole region in 2 dimensions. So what do we have here? We have a region in R2. So now we have to deal with this as a 2-dimensional object instead of just an interval segment. And then here's our differential. But our differential, at least the differential that we learned, has dx, dy, right? So what we need to make note for ourselves is that dA actually stands for dx, dy. So something that has a dx in it and a dy in it. But we'll see later that the order might make a difference here. So sometimes this might be seen as dy dx. And so in those cases, we'll dig deeper into that. Well, we'll dig shallower today when we're looking at dx dy. But tomorrow, when we start talking about integrals over general regions, the dx dy and dy dx will make a difference for us. Okay, and so those are the components. The 2 integral signs, well, obviously means we're probably going to be doing 2 integrals. But theoretically, or according to the definition, all we're doing is we're adding up a whole bunch of things and then taking the limit, and then so that we can add up an infinite number of things. But let's take a look at the idea of adding up a finite number of things, because we kind of did this with rectangles back in Calc 2, right? So we could do the same thing here, but the picture here is going to be a little bit weird because we're, again, going to restrict ourselves for today with just rectangular regions, but tomorrow we're going to dive into more general regions. So what we're really kind of interested in doing is for each of these, it's hard to look at like this in 3 dimensions. So why don't we take a 2-dimensional view of this where we're just looking at the x and y plane. Well, we break this up into little regions. And then for each of these little boxes, maybe I'll choose a different color here. I randomly select maybe a box somewhere in the middle. Say for that box in the middle somewhere, what I want to do is I want to find the height that goes up to the surface. And since we're estimating, we don't want a curved top, we're just going to have a flat top. But in that flat top up here, what we need to do is we need to choose one point. Let's blow this up a little bit. So this is a blown up view of this thing. And what we're interested in is we need to pick an actual point, one point from that rectangle, whether it be a corner here that we're going to plug into the function that's going to give us the height of that box. Well, on the other hand, we can pick from a different corner that will give us the height of the box. Or even more interesting, we can pick the very middle of that box. Technically, we can choose any point in that box, including any of the boundaries. But the most popular ones are usually one of the corners or the one right in the middle. Do you remember doing that? All right. Let's do a quick exercise to see how much you remember. I was going to split you guys up into groups, but it's no, let's do it anyways. Let's go split up into groups. But you don't have to move. You don't have to confer with your other people. One, two, three, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. And 1, 2, 3, 4, 5, 6. Okay. You guys have your numbers. So the first set of sixes will be one group. The second set of sixes will be another group. The third set of sixes will be the third group. And then the fourth set of sixes will be the fourth group. Do you guys know which six you are? You're the first set of six, right? All right. So what we're going to do is we're going to do a problem, attempt to do a problem here. And I know you don't have much more information. This is a rectangle that goes from 0 to 4 and then -1 to 2. Maybe I should draw the XY axis first. So 0 to 4 in the X, 0 to 1, 2, 3, 4, and then -1 to 2. So this is my rectangle, and I want to find the integral, the double integral of this function over this region. And then they want us to break M up into 2. So I'm thinking M is your X values. And then your N is your Y values. So that means I need to break up my X values into 2 pieces. So the 2 rectangles that I would have, if I just broke this up into 2 pieces, would just be this one going from 0 to 2 and then 2 to 4, right? And then my N is going to be broken up into 3 pieces. So it'll look like this. So you guys each have a number. I'll number this 1, 2, 3, 4, 5, 6. Okay? So for each rectangle, I want the first group to use the lower left corner, group 1. So find which rectangle you're in, and then use the lower left corner. Group 2, you're going to be in the lower right corner. Group 3, and then group 4. So I want you to find out your Z values. And then so you're going to have one value for this. And what you would do is you would add it up. Everybody in your group would add up all the values that you get. Okay? And then after you do that, I want all of you to go to your, again, respective boxes and figure out what the midpoint is of that box. All right? I know there are very little instructions here, but see what you could do. Talk to some of the people in your group, or maybe not in your group, and see if you understand what it is I'm asking you. All right, I'm going to give you 5 minutes to get started. Which one are you? Number 1? Lower left. So your point is going to be 0, negative. This is your axis. Okay. Now you're going to take that point and put it into the equation, and then you're going to get your height. Oh, that's the function. Yeah, that's the function. Okay. And then what you need to do is you need to add up yours with 5 other people. So what we're doing is we're looking at the function, is it 1 minus x times y squared? Okay, so it looks like we're in the first quadrant, right? Or mostly in the first quadrant. It looks like there's a lot of going down business happening here. So what I'm going to do is I'm going to create a region in this program where the y value goes as high as 2, and the y value goes as low as -1, and then the x goes from 0 to 4, right? And then I need to copy this function again. It's 1 minus x times y squared. So if I have two pieces in my x and three pieces in my y, I have to redraw this. And I need to get my, I need to have this bigger. Partition height by the left side. Left, upper, lower left, lower left. These are the rectangles that we get. By the way, the XY plane, let me just show you where the XY plane is. Oh, crap. Four. What goes all the way up to four? The X or the Y? X goes all the way up to four. Yeah, I can't see it though. -2 to positive. Let's go 6 also. So that's the XY plane, and just to let you know, it's possible to get those boxes below, right? Those are the boxes that you put into the function that got negatives. So this is what we have. We have some negative boxes, some positive boxes, but all totaled at the end, it looks like with the lower left corner, we ended up getting 4, positive 4. Right? That's what you guys got, positive 4. Now, if we choose the lower right, we got negative, did we get negative 12? Well, let's check. I think we got negative 4. I don't know if we did this right. I don't know if I did this right. Partition type, outer. So those are the points now. I asked them to show the points. And if we look at this from the top, we're looking at the lower right-hand points. And I think they got negative 12. So I don't know if we did something wrong, if they did something wrong, but the answer probably should have been negative 12. Let's try the upper left. Negative 8. Okay, so so that one looked like it was correct. And let's try the upper right. Negative 48. So this is the ones where they got, what do you guys get, negative 15 or something huge like that? So they contributed a lot of negative values. And so we have a couple of positive values up here, the positive ones that people got, but most of it was negative. Okay, so are you able to see the picture? So what I'm hoping is I don't think we were that successful. I don't think I was that successful in conveying the information about the Riemann sum and picking the points. But that activity hopefully got you to think about depending on which point you pick, you're going to get some sort of approximation. And so what we would like to do is we would like to, if you increase the number of partitions in both directions, you're going to get a more and more exact answer, right? Just like we take the number of triangles, if we increase the number, or rectangles, if we increase the number of rectangles, we get a more exact value. So let me show you. Iterated integrals. Let me show you this problem. Where we're going to use what's called an iterated integral. So what we're going to do is we're going to identify the x and y limits of your integration. Okay, so this thing now, the double integral over r, is going to break up to two separate integrals. One of them is going to be an integral, let's say with respect to x, where x goes from 0 to 4. And what we could do is we can integrate this with respect to x from 0 to 4 first. And then what we will get here is probably going to be a function with respect to y. So for each fixed y value, you're going to have a function with respect to y of the area in x. And then now you're going to integrate this with respect to y from -1 to 2, and then you would get your result. So an iterated integral is an integral where you work from inside out. And in the inside function, in the inside integral, it's possible that you're going to get an expression with the other variable in there. So let's try to do this. So what do we do with the y if we're integrating with respect to x? What? Guess? Just pretend it's constant, right? Just like we did for derivatives. So let's integrate this with respect to x. The integral of 1 is going to be what? X. The integral of x times y squared is going to be what? It's x squared over 2 times y squared, because y squared is just a constant. And we need to integrate this from 0 to 4, evaluate it from 0 to 4, right? So let's put 4 in there. We're going to get 4 minus 1/2 times 16 times y squared minus 0, because when you put 0 in for x, you're just going to get 0. And let's just quickly simplify this. 4 minus 8y squared, right? Now let's integrate that from -1 to 2 with respect to y. So this is going to be 4y minus 4y cubed, and let's call that 8/3 y cubed from -1 to 2. So we get 2 times 2 is 8, minus 8/3 times 2 squared is 8, minus -1. So that's 4 minus 1, or 4 times -1, minus 8/3 times -1. All right, what's this? Oh boy. So 24 minus 64 is 40. Is that right? 24/3. 8 times 8 is 64. 24 minus 64. -40 thirds minus. So this will become a plus. 12. 8 minus 12. Negative what? 8 minus 12. What? What's the final answer? Just 12, period? -20 over 3. So what's this approximately equal to? Like 6 point something, 7 point something? 6. So 6 point something, 6.7-ish. Our approximations were pretty far off. Again, because our approximations relied on really big chunks. But let's take a look at this approximation that they have on a computer, where we have 34 in the x direction and 40 in the y. So it looks like it's -13. Wait, that's not too close. What? -12? So it looks like it should be -12. So -13, that approximation of -13 is closer to -12. So that means it must be going in the right direction. Okay? So I urge you to try to look over this stuff. And then tomorrow we're going to take a look at more general regions. So this is the easy integrals where you have rectangular regions. When you start integrating over more general regions, it gets a little bit more tricky. So, okay. All right. See you guys tomorrow.